I think we can start now. Is everybody there? It's 8:20 on California time, and according to my schedule, it's time to begin. So each speaker will have 15 minutes, and I will rudely cut you off if you try to go significantly beyond that. So let's begin. Our first speaker is Michael Stutzer from the Leeds School of Business at the University of Colorado in Boulder. So Professor Stutzer, take it away.
Yeah, thank you. And let me arrange the screen a little bit. So I'm more planned on 20, but we'll just move through there. So I'll skip a little bit of literature review. And so if I don't mention some names here, don't be upset. But basically, I over about 20 years ago, I said for the last 20 years, or last 30 years, actually, I'm getting older. I have developed a sort of started and proceeded on and worked with others and tried to promote a kind of a unified way of using entropy in three big problems in asset pricing research. One is derivative securities features, like what is the price of an option? Many people have heard of the Black-Scholes option pricing model. I came up with a different way of using entropy to try and come up with an empirical way to do this based on observed prices of actual securities, trying to price an option sort of as an empirical method based on a past returns of that option or some other information you might have about it. And that has been followed up in the Journal of Futures Markets by a number of others. So this work has been picked up and extended by others as well. So I'll show you a little bit about that. There's estimation and testing of asset pricing models, much bigger thing that's done as a core subject in financial economics for people who specialize in that in economics departments as well as in business schools. That's work I did starting in conjunction with Yuichi Kitamura. Some of you are familiar with that, and other people like Guido Imbens and Professor Smith, who might be present today, Professor Atsu, a colleague of Yuichi's, and a relatively recent addition to this is an amazing person named Anisha Ghosh, I should mention, who's a professor of finance at McGill University, who has basically on her own figured out all this stuff and extended it with a series of co-authors, but she definitely does most of the heavy lifting there in a lot of different areas. So I think you'll be hearing a lot more from her in the future. And she's had good luck on publishing this stuff in so far in business school, the main business school finance journals, unlike me, who has not had such good luck at that, although having some. All right, and then also basically what I developed as an offshoot of this is an optimal portfolio choice approach for long-term investment, like if you have you're trying to come up with a retirement portfolio, for instance, and that is based on the same kind of mechanics and math you're used to using, but there's a frequentist interpretation of entropies that comes from the statistical theory of large deviations, and so this idea makes no sense without the large deviation approach. It's inherently frequentist. The others you can kind of rationalize by usual kinds of information theoretic and Bayesian sort of reasoning that many of you use in your work. But the large deviation approach is critical to this. That was a work I did in the journal Econometrics and also more recently in the physics journal Physica A, Statistical Mechanics and its application, because those people are familiar with this foundation for statistical mechanics and the theory of large deviations and entropy there. It's a hotter subject there. Okay, so we have our old reliable, the linear inverse problem in many of you work have done something that can be reduced to this kind of problem as rationalizing what you did. You find a measure which minimizes a callback-Liebler statistic of Q relative to P, subject to a bunch of moment constraints on the thing you're looking for, the Q, the one closest to P in terms of relative entropy or the callback-Liebler statistic, with a series of constraints here, expected value constraints. All right. Now, in derivative security prices, the application, obviously I can't describe everything here, but in 15 minutes, I can certainly give you the notion. The application here of these moment constraints are that the expected value with respect to the Qs you're looking for, not the reference measure P, which are actual probabilities of states of nature rather than these these transformed ones. The constraints are going to be that the expected log gross return of the stock has to be prescribed constant where the prescribed constant is going to be the value of a usually called a risk-free asset in finance growing at a rate called the risk-free rate of return, in which case this Q is called a risk-neutral pricing measure. So it's a way to, basically I worked on an empirical way to estimate a risk-neutral pricing measure from a set of securities prices, say a set of returns on a stock, you're trying to price an option on that stock and you have its historical returns. So you kind of put that into this black box. Out from this black box of solving this linear inverse problem comes a set of risk neutral probabilities, and then the value of a derivative security like a call option on the terminal value of that stock will be the value of that will be the value of its terminal payoffs at expiration, discounted back to the present using the risk-free rates. It's kind of familiar to those of you. There's actually an example like this done in Amos's most recent book. And I know that because I looked at the example and made just to, not that Amos needs a lot of checking on whether he does calculations right, because he didn't, but I think Amos felt better. It's kind of if somebody else had verified that. And he had it right. All right, so that's going to be the price of your option. So this is this work that's been carried on, as I said, extended in the Journal of Futures Markets by a number of people, as well as some other places. All right, estimation of parameters and testing of asset pricing models, like say the consumption-based asset pricing model, other types of asset pricing models. These you have a set of restrictions in these theories, and this does not have to be just asset pricing models. It says the expected value of a bunch of random variables given a true value of an unknown parameter vector has to be equal to a set of prescribed constants. In risk neutral value, this is kind of the stock and trade of many models where you can reduce it to something amenable to the generalized method of moments estimate of Hansen. You have to be able to put the problem in this form first. So this is a alternative to Hansen's method for estimating parameters in models like this. That Yuichi Kitamura and I developed and has subsequently been developed by many others and worked on. All right, so you have this. Then there's going to be an auxiliary problem here. Again, here comes your linear inverse problem. Find a measure Q, which will make, find a measure Q, which will be closest to the actual measure P, the data generating mechanism does for these moment conditions, if you knew the true value of the parameter. Find a measure Q closest to P, subject to actually satisfying these moment conditions. So if in fact you were at the right parameter measure, you didn't know this measure P, Q would be equal to P and you'd be 0 here. But in practice, you won't be because you're not at the right value of the parameter. That's why I stuck in a theta here, which is untrue. But you can warp the measure so that it is the case. And the idea is to solve this auxiliary minimization problem we showed. So it's starting to look like a method of moments problem where you minimize some kind of function with respect to the parameter vector. It's not quadratic in this case, it's a callback statistic derived by first minimizing with respect to Q, solving this linear inverse problem. So you solve this linear inverse problem a zillion times, each one for a theta, you find a theta that gives the minimum value of that thing, and that's your parameter estimator. So that's been subsequently named the exponential tilting estimator. And the relationship of that to Hansen's work is derived in our work as well as many others. And I will say that while it competes with Lars Hansen's method, he actually likes this approach. And he says nice things about it. And he sees that there are some advantages to doing it this way versus the squared error kinds of criterion that he used in the generalized method of moments. If you reverse Q and P, you get something not called exponential tilting, but you get something called empirical likelihood. There's an enormous literature on that. So those are those problems. And now in my time remaining here, let me talk about something that is not so obvious, which is portfolio choice that minimizes asymptotic shortfall probabilities. And there's lots of different ways people have tried to do this over the years. And I came up with my own way. So again, here, the problem is going to be you've got some x's here, and in this case, the x's depend on a parameter vector. The parameter vector are going to be proportional weights you place on different assets in a portfolio. And I invest 10% in the S&P 500, 20%, maybe nowadays, I suppose you invest 90 in the S&P 500. People think the stocks are going to be so great in the future. 5% in some bond index and 2% in something else, this kind of thing. So these percentages are going to be the thetas here. The thetas are going to be weights, and they could be negative or positive if you allow short selling. And it's not going to be obvious why I'm doing this, but there will be a set of linear restrictions, again, EQ of x1 equal to prescribed constants, okay? And so there's going to be a linear inverse problem. And in this case, it's going to be minimize the callback Weibler statistic with respect to Q. So again, it's the entropic solution of that linear inverse problem that many people do. Linear constraints, minimizing callback Weibler. And now, and once we get a solution to this, we're going to find a theta that makes this as big as you can. And that's going to be our vector of portfolio weights that turn out to minimize the asymptotic shortfall probability of this with respect to the stochastic growth rate of the portfolio. It's going to make that a minimum, it turns out, if you read these papers. Now, the question is why? So that's where you have to understand the statistical theory of large deviations. How does entropy turn up in a problem like this? It doesn't sound anything like that. So here's the reason, okay? The X in this case is going to be the log gross return on the portfolio at time t over the next time interval. And so if you take the time average of that, that is the time average log gross return. That turns out to be the stochastic growth rate of a portfolio. And asymptotically, that limits to a number for these kind of strategies, which would be the expected log gross return of that portfolio per period. All right, so here we got a period model. This is going to be a random variable, although as t goes to infinity, by the law of large numbers, it's going to converge to something, which is the expected log gross return of that portfolio. All right, so we have something like that. And the probability that'll be less than or equal to C in the case where you pick one with a high enough expected log gross return to exceed this vector C. It turns out that is going to be equal to a function which exponentially decreases at a certain rate I. Okay, and so it turns out this probability will go to 0 as t goes to infinity. That's desirable here. The shortfall probability will disappear, but we want it to disappear at the fastest possible rate. That's our heuristic idea for minimizing shortfall. We pick a portfolio strategy, which is a vector of portfolio weights theta, which makes that portfolio shortfall probabilities go to 0 at the fastest feasible rate. Okay. Now to compute that rate, this is given by large deviations theory. You compute this particular function, and you see here the log of the moment generating function appears. That's called the cumulant generating function of the vector x here. And it turns out that that rate is in fact this minimum value of the callback Weibler statistic. So the entropy problem comes in, you solve this linear inverse problem, you find the theta that makes this thing as big as possible because it will depend on it. So it'll be a different Q for every theta. But the actual rate itself, which is a performance statistic for this portfolio, is in fact the value of the relative entropy. So the relative entropy comes into this frequentist problem and in fact gives you the solution. You have to be able to do it, and then you have to plug it in at the when you find the biggest value of this. That's going to be your optimal portfolio theta star here. So it has a frequentist interpretation. So in general, if you have an IED portfolio strategy, you get this. That's what I just showed you, relative entropy. If you don't, large deviations theory shows you how to generalize this calculation. You can see it looks somewhat similar, but somewhat different here. And you could think of this as being a generalized entropy, which is how the literature does in large deviation. And so if you have a problem where the portfolio strategy is not IED, the returns are varying over time in some way, in an ergodic way, which is widely used in finance theory, then you have to do this a little bit differently. But all it does is change the calculation of this I and the fact you no longer have the callback Weibler statistic, but sort of a generalization of it. All right.
Michael, 1 minute.
Yeah, we are done.
Oh, good.
Yeah, so we're done. I just want to end with this diagram. Here's Claude Shannon. He is clearly not equal to Ronald Fisher. All of your talks show this. You don't use Fisherian techniques. Many people like the Shannon type or callback type alternatives there. Well, what I have now showed is that he is not also equal to Harold Kramer, who was arguably the founder of large deviations theory, where he showed how the entropy has this frequentist interpretation. in the ID setting, and it's been subsequently generalized. Okay, so I am done now, and if you want, I can stop sharing. Would you like that, John, and just go to our screen?
Yep. Thank
Okay.
you, Michael.
Okay,
Very
we're
nice.
back to the screen now.
Our next speaker is Wojciech Spankowski from the Center for Science of Information at Purdue. And he is going to talk about precise minimax regret for logistic regression. So Wojciech, take it away.
Okay, let's see. Do you see my slides?
Yes.
Okay, great. Thank you very much. Hello to everybody. It is 155th birthday of Shannon. So let me talk about applying information theory to machine learning. The joint work with my friend Philippe Jacquet from India and Gil Shamir from Google. And some of this work was done when I was in Google. So let me give you a very general introduction. It is online learning, so data comes in sequentially, and they are used to update the model, our knowledge about the model, and the predictor. We are talking about supervised online setup. It means that we already trained the model with some data, and we have some information about the model. And the data come in rounds, and I will denote by T, the T rounds, and they go from 1 to capital T. And they predict the label YT based on what we've seen so far with terms of labels, and actually data on feature up to time T. Once I predicted the label is revealed to me, and I incur some loss. And we will discuss only logarithmic loss, actually logistic regression, which I explain in the next slide. Just for notation, T is the number of the rounds, capital T is total number of the rounds, and I will use upper index Y of T to denote a vector. So let's explain this in terms of a game between a learner and a nature. So at each round, the learner obtains a d-dimensional, that's important, d-dimensional future vector, xt, and makes prediction that I denote YT hat. The nature then reveals to you the real levels. By the way, all the levels here are binary -1, 1. And of course, when that happened, I incur a loss at time t. But the total loss, and by the way, the loss I will denote in general L Y hat Y. So the total loss is the sum over all rounds. But instead of computing this way, we compare it, so the relative loss, we compare it to the best predictor or the best loss done by some experts. Let's say you use some predicting function f that belongs to some class of references. It doesn't matter what it is right now. In this talk, what we will go one step more. This is pointwise regret. Capital R is a pointwise regret. We will maximize over all possible label sequence and minimize over the prediction or the how we do prediction. This is called maximal because of this marks, minimax regret. Okay, let's go further down in the specifics. We only consider linear prediction. W characterize the model as a weight. XTW here is the scalar product. And the loss function that we consider as logistic regression, defined here as log of 1 plus exponent. YT is the label, -1 plus 1. And the scalar product of XT and W. We do a little bit more. We assume that we do prediction based on the learning distribution Q, which is a function XT and YT -1. And so the first total loss here is right now expressed in terms of this learning distribution, which I don't know. And we compare to the best predictor by doing info over odd W. W express in some sense our knowledge about the model. In the minimax scenario, we were trying to find the best predictor for the worst sequence of point-one regret. Notice that because of this is the lower bound for the point-one regret for all possible sequences. About Q, in most cases, Q is some kind of Bayesian estimate, we do not assume it here. We could have whatever we want. Okay, so yes. So then, so this expression is a little more complicated. So let's start with something simple. I will assume now that the feature values can take only n distinct value. Imagine this way: you have an alphabet, finite alphabet. At every time, a feature picks up d values, and this creates you a vector aj. But there are only n distinct feature vectors. That's important. That means that for every feature aj, there will be t sub j times that it occur in a round of size t, and the ratio is alpha j. So here's the expression that what we have to do. Here I put absolute loss function is the total loss over t rounds, except that because we are having only n different values, this expression becomes a little more complicated, but in fact, it's a little simpler. So you can see that there are two parameters, the feature values and the number of times it occurs in a total number of rounds. The next thing that we should note is that the logistic regression has some interesting thing, that for binary labels, I can express probability of the label, conditional probability of the label, as 1 over the logistic expression, 1 over exponent yt, xt, yt. Now, so what is the total probability of seeing yt, y1 to yt, label vector, knowing feature and weight? What it is, of course, it will be a product over all possible feature values. But notice that whenever xt is equal aj, I still have to choose yt. It could be +1 or -1. When it is +1, I'm assuming that out of tj values, kj of them are equal +1 and the rest are -1. That's why we have this expression. So, and together with this will help us actually to represent regret as the following log of two ratios: supremum over all weights of the probability that I just showed to you, and q. We don't know q. So because of this, we're going to go to minimax scenario, and we will try to find the best q for the worst input sequence. This expression is a little unfriendly, so let's try to do something and try to find a better expression for that. So first of all, we define maximum likelihood distribution, which is the supremum over W of this probability, and normalize. This sum we will call Starkov sum. This normalizing sum is important. Then let's look what we can do with the minimax regret. I repeated the first line, the definition. Now, sup and max commute, so I can put sup here, actually after log even. And now I will do a small trick. This sum, I will take log of the sum and add it and subtract it. The subtraction is P star already here, okay? So I added and subtracted the same term. Now, if I choose Q equal to this maximum likelihood distribution, that is 0. And what I'm getting is that my minimax regret is equal to log of this red sum, which is called the Starkov sum. In information theory, source coding, compression, we usually dealt with this, but we didn't have xt and weight, so it was a little easier. So in summary, we represented the regret as the log of the Starkov sum, and now I'd like to understand how this behaves when t grows and when t actually is getting bigger and bigger. So let me first summarize a little bit of literature. D equal 1, we can see as what information theory was doing in universal compression. For alphabet size m greater or equal than 2, Davison introduced in some sense the minimax regret, average minimax regret. Starkov introduced maximal minimax regret. Some first result came from Krzyzewski and Trifomov, Rissanen. And with my friend Michael Dmota in 2004, we basically summarized all what is known, getting actually full asymptotic expansion using another combinatorics. This was for M fixed. when M grows, things are interesting. Olitsky and Santana start introducing that, and they were able to get some results for M growing with M in two regimes, but not in all possible regimes. Shamir did the same. With Marcelo Weinberger using saddle point method, we were able to get, in this particular case, which we call minimax the redundancy, we get full asymptotic expression. But the interesting thing and the new twist is when D is greater than 1. This looks very different. For Bayesian algorithms, remember, we do not assume it, but for Bayesian algorithms, Kakada and Geer, they actually gave an approach how to get this for fixed D, pointwise regret. Foster did it for pointwise regret, but not even for binary for general M, but finite M. And Shamir in Colt 2020 actually get it for large D. What we do in this paper, we start introducing this minimax regret with Gil. And just 2 weeks ago, I presented part of it in algorithmic learning theory, but today I will give you a little more because actually we understand much more for much more general case. The closest that we can see, it is related to something that Rachlin and Sridharan, they did, but they also do maximization over XT. If we do it, we expect to get the same result. Okay, so let me tell you a little bit about how I'm doing with time. Okay, I should be okay. So let's consider the first simple case that I have finite number of feature values. AJ, that is a vector, and I have only n distinct vectors. Okay, each vector is d-dimensional. Let me introduce a simple function, which is like a logistic regret, but it's 1 plus E minus W, 1 over, and Q is 1 minus this one. So what we can prove is that when n, the number of distinct feature value does not grow too fast, smaller than the square root of t, for fixed dimension, we are getting expression that for information theory it makes sense. Part of it. The first part is d half log t. This is basically we pay for every unknown w component of the weight, and you have d of them, 1/2 log t, and because we have d unknown vector, that's what we pay. There is a constant, but this is the new thing that come up with logistic regression, and it's quite complicated. It is a B here is a d by d matrix that have this function P defined over here, over the scalar products, and you have a tensor product of the feature vectors. This, I can represent this B in a little different way that if I have time to give you a proof, I will actually explain why this A is important. Let's see how we will go.
We have 2 minutes, Wojciech.
2 minutes, okay, so let's go. And let's consider, so first of all, we can generalize it to a general alphabet, not only of alphabet size 2. And actually, in this case, W should be a matrix. And you can see that you have similar expression. And M-1 occurs in 2 places. But I want to tell you this one, that is important. So 2 more slides. When the feature vectors are anything that you want, let's say in banded 3-dimensional cube, then we can prove, and this is very recent, that for D that grows not faster than T to the power 1/3, we're getting similar expression for minimax regret. There is a constant, but this constant is function of T and feature value. This constant looks like similar as before. This is a D by D dimensional matrix expressed here. You see, I don't have alpha, I have 1/T. So the questions happen how this CD behave. And this is my last slide. So what if we assume that the feature value data lie on a sphere on a board, d-dimensional and d is large, we could compute precisely these 2 constants, and that minimax regret behaves as expected from information theory. Remember, D is like size of alphabet information theory. So D half log T divided by D when D is large. And I think I finished here. Okay. So
Perfect.
let's finish here.
Just on the minute. Thanks. Our third speaker is Ariel Katicha from the Department of Physics at the State University of New York. And the title of Ariel's talk is Entropic Dynamics on Statistical Manifolds. So Ariel, take it.
Okay, let me just start it. Very good, here we are. Can you see it? Can you see my cursor?
Sure.
Very good. Well, very happy to be here. Too bad that we didn't have to travel. Much rather be there in person. Okay, I'll be talking about entropic dynamics on statistical manifolds. This is joint work with Pedro Pessoa and Felipe Xavier Costa. So let me start. The big question that I am involved with is science just a framework for processing information? Or rather, it's really just a description of what's really going on. A little bit of my background, my field is physics, and the program in which I have been invested for such a long time now is to derive laws of physics from principles of inference that lie outside of physics. This is where entropy comes in. Of course, if the principles of inference from which we derive laws of dynamics, like the Schrödinger equation, for example, lie outside of physics, then we can try to apply the same principles of inference to fields that might take us beyond physics. So our goal here is going to be to construct dynamical models as examples of entropic inference. So I want to illustrate the general principles in very, very simple cases so that you can actually, perhaps, hopefully, see that you can change things here and there and make the whole framework available to your own field. In particular, one of the things that I would like to stress is that what generates by working this way is a mechanics, like the Schrödinger quantum mechanics, but doesn't rely on underlying mechanisms. And this is what might make it useful in fields beyond physics. So what's our subject matter? The idea is that the true states of a system are its microstates. But we want a coarser description in terms of macro states. So the macro states, the coarser description of the system, are going to be probability distributions over the microstates. And those probability distributions, those macro states, are going to be labeled by expected values of certain functions. Depending on the field, you would choose different functions here. Rho is a probability, you take an average. What labels the macro states is these variables capital A. And there are several of them. You can have as many as you want. If you wanted to do thermodynamics, the micro states are the positions and momenta of atoms. The macro states could be, for example, states of thermal equilibrium. These functions here could be like energy. So one of the variables you might want to consider is the expected value of the energy. So how do we figure out these probabilities? You maximize an entropy. You can recognize it as being minus the Kullback-Leibler divergence. Relative to some prior, in physics, most of the time, we like to choose an equal a priori probability postulate, but you don't have to do that. So the macro states that result from this are give states. And here we have it, the probability of the micro states conditional on those parameters, those variables that define the macro state, are given by, there is a prior here, there is the exponential with Lagrange multipliers and the functions that you have chosen that capture the relevant information to your problem. I'm going to use this notation that's very common among physicists, in which you put indices downstairs and upstairs, and you sum over them. There are many of these guys, there are n. So repeated indices imply a summation. And then, of course, you normalize everything. That's Z is the normalization factor, the partition function. It may seem to people that this looks very much like thermodynamics, and of course it does. But as you well know, this is just a manifestation of having maximized an entropy. It has nothing to do with physics. That's the point I want to emphasize here. These functions have been discovered in a wide variety of situations. They're also known as the exponential family, and the functions A that capture the relevant information to your problem end up being the sufficient statistics. So we can now go ahead and compute the entropy of this give state, and you get something like this. Remember, there is a summation here, and you can estimate what the Lagrange multipliers are by solving an equation of this type. And the Lagrange multipliers that appear receive a very nice interpretation as being basically the gradients of the entropy. This is familiar. Now we start the talk. The space of macro states, which I'm drawing here, I'm just drawing 2 dimensions, is such that any point on this space is labeled by these expected values. I'm going to have coordinates like A1, A2. In general, I would have like an n-dimensional space. And this expected value here, this point in the space of macro states, actually represents a probability distribution. This is important. What this means is that the space of macro states is actually a statistical manifold. Every point is a probability distribution. And the reason this is important is that this type of space, this type of manifold, acquires thereby an incredible amount of structure. It's not just any space out there. It is a space in which each point represents a probability distribution. And that means that if you have neighboring points, you can compute a distance between them. And the distance is sort of unique. You can't fool around with this. Otherwise, you violate certain desirable features you want on probability distributions. The way we write a probability distribution is by some generalized version of, the way you write the distance between those 2 points is some sort of generalized version of Pythagoras theorem. You can see that you have squares on the right-hand side, you have a distance, a short distance on the left-hand side, and then you have all sorts of wacky coefficients that reflect the fact that these spaces in general are going to be curved. The actual metric tensor ends up being, for these give states, particularly simple. It's just the Hessian of the entropy. So this is relatively easy to figure out. And it has you can also figure it out as being a derivative of the Lagrange multipliers. Very good. So on this space, we would like to study a dynamics. We want to see how things move around here. Oh, okay, yes. Another detail that's going to be an important notation. If you can figure out distances between 2 points, then you can also figure out areas and you can also figure out volumes. The volume that you have on this space is going to be written by an expression like that. You can probably recognize the measure here. Trivially, the G is going to be the determinant of the metric tensor. So this is something that you can also compute from your entropies. Very good. What we would like to see is how there might be a dynamics on this space. And the way we do it is by saying, look, if you have a point, what we are going to try to figure out is how you're going to evolve away from that point. And the basic law here is there is no law. Change happens. You're going to jump, and I'm not going to give you a rule of how you jump. I'm going to give you a rule of how you do not jump, which is much easier. Basically, what we're going to be doing is jumping from one give state with coordinates A to another give state with coordinates A prime. And what we want to figure out is a transition probability in which you go from microstate X and macro state A to the corresponding states a little bit later. So how do we do this? This is where we come up with a form of entropic dynamics. And we say, we're going to compute this transition probability, we're going to maximize the joint entropy. So these P's and Q's are the joint entropies. You can see here in the integration measure that what I'm really interested in is distributions of A prime and Y prime, the probability of where you jump to. So what is going to be our prior? The prior is going to be that the motion is going to be continuous. So, and this is a tremendous simplification. The fact that the motion is continuous means that you can analyze motion over a longer step by as a succession of very short steps. So we're going to write the prior, which is here. First, we just use the famous product rule of probability distributions, the probability of the first variable times the probability of the second conditional on the first. That's what I wrote here. And I'm going to say, whatever this is, it's a probability of where you're going to jump to. This is just the old prior that we used in order to figure out the give states. It's basically you're just saying, I have no idea, I'll jump anywhere. And for this guy, this is an interesting one because this is telling you you're going to jump from A to A prime. I'm going to assume you jump a very short step. When you do that, the distribution that you get that is maximally uninformative is going to be something that says, look, you're going to jump, essentially, this is just a volume measure. You're going to jump essentially anywhere, except you don't want to jump far away. These are short steps. So what I'm writing here is it's going to be a distribution that is spherically symmetric, no correlations at all. And you see that this Pythagoras theorem here, this is just the distance. But I'm going to assume at some point that this tau here is going to be taken to 0 so that you have infinitesimally short steps. Whenever we consider something that involves infinitesimally short steps, what that means is that ultimately your equations of motion are going to be differential equations of motion. This is what Newton did back in the 17th century when he introduced the notion of derivatives and accelerations in order to do physics. Basically, you say, look, motion in general is complicated. Take short steps. Those are much easier. And then integrate. That's what we're going to be doing. This is the prior. Short steps with no correlations. Now we're going to really introduce the constraint on the posterior. You see, it's the same joint distribution. Basically, we had for the prior. We separated into the probability of A prime and then the probability of X prime given A prime. And we're going to analyze these two terms separately. This is the probability of the microstate. This is the constraint that I'm going to impose. This is where I would say the physics of the problem is being introduced. What I am going to say concerning this, how I'm going to constrain this term, this factor, is to say, look, if I give you a prime, then the probability X prime is given. It's given by the fact that you're going to move from one point A on this statistical manifold to another point A prime that is also in the same statistical manifold. This is the constraint. You're going to evolve, but you're always going to remain within this space.
Ariel, 1 minute.
Yes, okay, very good. So the transition probability, you compute it, and there are two terms here. One of them that says, just maximize that joint entropy. One of that says, look, you're going to try to go in the direction of maximizing an entropy, but you're going to do it in short steps. That's all there is to it. Then we need to introduce time as a way to accumulate many of these small changes. And the way we do it is we say, look, if you are in a certain probability distribution, you use a Markov kind of distribution integral here, and you get your final distribution. So let me write this as a function of, write these expressions as a function of time. So you go from a time t to a time t prime. And this integral equation, which is like a Chapman-Kolmogorov equation, can be rewritten in an integral form, which is, as you see here, it's some sort of equation for probability distributions evolving, conservation of probability, where the velocity of these probability distributions includes two terms. One of them is a drift component that tells you you're going to move in the direction of increasing entropy. The other one is an osmotic term that says you're going to have a diffusion term going on here. And this is why the equation looks like a Fokker-Planck equation. And this is basically the end result. There are these two terms, two opposing tendencies, one to go up the entropy gradient, another to diffuse, so that probabilities never concentrate too much. Let me give you an example to conclude. This is the simplest possible toy example you could imagine. The statistical manifold refers to a three-sided die. So if you impose a normalization of the probabilities of this three-sided die, you are living on a two simplex. The dynamics is given by this Fokker-Planck equation, and the velocity includes these two tendencies. So if you want to see what the drift term looks like, you get something that tends to pull you towards the center of the simplex. This is
nice, Ariel.
Evolve. And if you ask for what is the equilibrium situation, well, you're going to try to go to the center, but there are these derivatives in the second term, the osmotic term, that say that if you go to the center, you try to concentrate your probability too much, you have a high derivative of probabilities. Look, high derivative of probabilities there. And that's going to push you in the opposite direction.
I got to stop you there, Ariel. Ariel, I have to stop you there.
Very good.
Two minutes over.
Equilibrium situation.
Maybe in the question period, you'll get a chance to expand on.
That's good. I'm done. I'll
Okay.
just put those there.
It's beautiful work. Very nice. So let's put questions into the chat. I will open up the chat room and.
Shall I stop my share?
Yes, stop sharing for now. And let me just ask people to either just write your name in the chat room and say you want to ask a question, or write the question down. Either way. Questions for any of the three speakers? Here we go. Paulo has two questions for Ariel. So Paulo, ask them.
I'll be very quick. I know time is tight. I really appreciated all of the talks. Professor Katicha's talk happens to relate a little bit more closely to my work. So hence my questions to him. My first one is, you are effectively making a Markov-like assumption on the process at the end there, which then takes you to a generalized Fokker-Planck type characterization of macro state dynamic evolution. But it appears to be far more general and based not on microkinetic specifications, but on simple probabilistic. I want to wrap my head around that because I think that's very interesting. So I understood that. Okay, cool. My second question is this. I'm also working on application of information theory to characterization of non-physical systems. So what you said about that is very interesting to me. In your talk, you motivated systems where, if you will, the regularities in the evolution of the system can be expressed as moment constraints over the domain of the system. In other systems, we may have regularities that may not be expressible as moment constraints. And I was wondering if you had any tips or insights on how to handle those. Presumably, there will be some kind of mapping to some kind of entropic measure that could capture the bottom line consequences of those non-moment regularities on a functional of the manifold, the Gibbs manifold that you're pointing to. But this is something that I'm trying to figure out myself.
Very good. Let me answer. There are two interesting aspects of the questions you ask, and I have to say that they're very perceptive, because this is one of the, these are two of the features of entropic dynamics that are novel and that offer great opportunities. One of them is, while it is true that our final equation ends up being Markovian, that is true. That is derived rather than imposed at the beginning. I didn't have time to go over the details. One of the features that's very interesting in this is that in the whole theory of inference, there is absolutely no reference to the notion of time. You can just make inferences about the future as the past. So inference is silent on the notion of time. So if one wants to invent a theory of dynamics based on entropy, then one has to actually invent a theory of time. And so the little tau that appeared there in my transition probabilities is going to be very connected with that. And typically one introduces time in such a way as to make the dynamics look as simple as possible. Now, my interest in this topic is to actually come up with a formulation of quantum mechanics that includes a derivation of a notion of time that is actually useful. And of course, you can see probably where I'm going with this. I'm including in the derivation of quantum mechanics notions that are coming from general relativity. Obviously, the eventual goal is to unify those two. The other question you asked was about the possibility of including constraints, information in the form of constraints that are not in the form of expected values. Yes, that's definitely possible. You probably even saw in my very quick presentation when I had a constraint. I had a constraint on the transition probability. That was not an expected value. The constraint that I imposed there was you remain on the manifold. So that was a very geometrical constraint. It wasn't an expected value. It's very much possible.
Yeah.
There is another aspect of these constraints that you might want to look into, because this is where quantum mechanics comes in, which is that the constraint that one imposes need not be the same every instant. It could be that one instant you impose one constraint, the next one different. And if you have these constraints being themselves dynamical, then the world opens up. This is how we get quantum mechanics. It's really like you have diffusion, but you have diffusion on a manifold that's itself dynamical. It's like diffusion on a water bed. You can have wave phenomena, you can have lots of interesting
Ariel,
stuff.
let's go to another. There's several other questions. I want to make sure
Very
everybody.
good.
Ira has been in the queue.
Okay, thanks. My question is, you're using the Fisher information metric, right?
Yes. Oh, is that to me the question?
Yes, to you, sir.
Yeah. Okay, good.
Now, the Fisher information metric is positive semi-definite. In your case, do you have to check that it's positive definite? Because this won't work unless you have positive definite. Is that what guarantee?
Oh, this yes, it is. You can actually be certain that it's going to be completely positive. Yes.
Okay, good. And what
yes,
is it?
No problem.
Curvature, sectional curvature analysis on the statistical manifolds that you build? Do you have any idea what the curvatures are?
Oh, okay. In some problems, yes. In these particular problems and that have to do with relatively simple dynamics on statistical manifolds, the expert on that is my student Pedro Pessoa, who's there. He has computed many of these geometries for interesting systems like what happens when you have Bose-Einstein condensation, what happens when you have phase transitions, and there are interesting phenomena there to be studied.
Okay, thank you.
Sure.
Okay. Let's see, Professor Lawless, you have a question, I believe.
Yes, you began by assuming that the microstates are independent of each other, which is something that Schrodinger would have liked originally and posed that in an angry question to Einstein who said, no, they do not have to be independent. And in fact, that argument led to Schrodinger and his equation. And his later conclusion, much later, 10 years later, that the whole can indeed be known and the parts not known. So how do you handle that problem?
Okay. As you clearly you understand some quantum mechanics, which is good. The issue of the interpretation of quantum mechanics has been an amazingly wonderful subject throughout the 20th century and well into the 21st century. And there are different interpretations. One of them, due to David Bohm, allows us to think of the particles as having definite positions at all times. So if the particle goes through a two-slit experiment, you know, the famous double-slit experiment, then the particle is going through one or through the other. But it's definitely going through one, definite positions. Now, what's interesting in interpretations of the type of Bohm, which is the one that which is related to the one that I favor, obviously based on entropic dynamics, is that there are all sorts of non-local correlations appearing between the particles. So there will be all sorts of non-local correlations. That takes care of the problems with violations of Bell inequalities and all sorts of things. So it is possible, this is my shorter answer, it is possible to have a fully quantum mechanical description of nature in which the particles have definite positions. This is what allows me to talk about the little x, the microstates, without any problem. But then, of course, in this particular problem, my point was not to say this refers to quantum mechanics. The constraints that I have to use for quantum mechanics are different from the constraints that I showed in my little short talk. For quantum mechanics, you have to complicate the model a little bit more.
Do we have questions for either of the first two speakers?
Yeah, I had one I wanted to pose to Stutzer, and that was on whether he's come up with anything comparable to Markowitz when a market is upset or approaching an upset. Has he been able to improve on Markowitz's notion of portfolio theory?
Yeah, muted.
Right, there we go. A rookie mistake. Although I've been teaching on Zoom here about a year, which is as long as I can remember nowadays at my advanced stage. Okay, well, the students probably like it when I stay muted. They don't interrupt. They don't interrupt to say I'm muted nearly as quickly as you did. So the answer is if you use this method, which seems kind of abstract and bizarre, and entropy arises as a frequentist sort of a number that has a frequentist interpretation. If you use it for the shortfall probability, and you assume the standard kind of model Markowitz did, which is that securities returns are normally distributed, or gross returns are log normally, the prices are log normally distributed. This is what really rationalized this mean variance stuff he did in the 50s. If you do that, then it turns out the criteria, when you do all the calculations, it's equivalent to maximizing this thing called the Sharpe ratio, and there's a risk-free asset. Well, that's something that also arises in his calculations as being the rational thing to do. So it turns out the entropy, when you go ahead and make all these calculations, it is in fact the same as maximizing this thing called the Sharpe ratio. So it relates to it, but only in that special case where his method kind of made sense from a philosophical, economic foundation. Samuelson did not like his ideas. He said, oh, I can conceive of lots of other things. And then why would we restrict ourselves the way Markowitz did? He actually kind of treated it like it was sort of lightweight stuff in the 60s and 70s when he developed the expected utility-based dynamic approach to portfolio choice with his student Merton, for instance, later on. Well, it turns out that in these other cases, I get something different. And so I can talk about what that is and how it relates to the result and so on. So that's my relationship to Markowitz. Your specific question about disruptions in this, no, I had not really considered anything explicitly like that, although I might.
Okay. As with every conference I've ever been to, there's never enough time for questions. We are out of time, and it's time for the next session.